Hello and welcome to our webinar. Today's topic is the new SafeTI Hitex Safety Kit. My name is Roland Pickel. I'm responsible for marketing and sales at Hitex. Before my colleague Dr. Björn Sander explains the basics of functional safety and the SafeTI Hitex Safety Kit, I would like to briefly introduce our company Hitex to you. Hitex was founded in 1976 in Karlsruhe, Germany, has become an expert in microcontrollers and is renowned for powerful in-circuit emulators and development tools. Thanks to its comprehensive microcontroller know-how, Hitex is in strong demand as a service provider. For our customers, we do hardware and software development, production and logistics, as well as test services, consulting and training. Based on our experience in many successful projects and our close cooperation with certification authorities such as the TÜV or the VDE, we have developed a broad knowledge of safety-critical applications. We accompany our customers from the concept phase through the whole project until the final product certification. In the next half hour, my colleague, Dr. Björn Sander, will introduce the new SafeTI Hitex Safety Kit to you. This kit gives easy access to the comprehensive safety features of the Hercules microcontrollers and is a good introduction to TI's safety concept. But enough of the introduction now. Please take over, Björn.
Yeah, thank you, Roland, for the introduction. As it was said, this webinar is about functional safety and specifically about the SafeTI Hitex Safety Kit, abbreviated as SafeTI HSK, and the purpose of this kit is to get you quickly started with the development of safety-related systems based on SafeTI components from Texas Instruments. First, an outline of this webinar. We quickly recall what functional safety is. Then I want to introduce you to the SafeTI concept from Texas Instruments. And then we come to the main part of this webinar, the SafeTI HSK evaluation kit. Here we will get an overview of the kit and then dive a bit into detail regarding hardware building blocks and the safety software stack. And before I come to a summary, we will have a live demonstration of the kit, and we will do profiling measurements and fault injections, and finally we will answer some of your questions. Probably most of you have come across the IEC 61508 fundamental safety standard, and as you can see from the picture on the right, there are quite of standards out that were derived from this fundamental safety standard. Among those standards, the famous ISO 26262 for automotive systems. The IEC 61508 defines safety as the freedom from unacceptable risk, and as functional safety is the part of the overall safety relating to the EUC and the EUC control system that depends on the correct functioning of the electrical, electronic and programmable electronic safety related systems. And in order to make this a little bit more practical, small example. On the right hand side you now see an electrical power steering, and you might know that within the IEC 61508 a safety life cycle is defined, and then hazard and risk analysis is part of this safety life cycle. And one potential hazard when we consider the system on the right could be unmotivated steering motions during the drive. And as we pass further through the safety life cycle, we come to the derivation of overall safety functions, and one safety function that could be assigned to this hazard would be prevention of dangerous steering angles. And it's then the task to implement these overall safety functions with safety-related systems, and you can do this with components from Texas Instruments, and you get special support with SafeTI design packages. Among those SafeTI design packages are functional safety-enabled semiconductor components, of course, but there is more. There are safety documents, tools and software, the corresponding safety development process and as well quality manufacturing process. And there are products, SafeTI products available in different categories. For example, MCUs, power management, safety companions, motor drivers, count transceivers and more. And some of these components deliver component level compliance up to safety integrity level 3 and AC level D with respect to IEC 61508 and ISO 26262 respectively. And many different industries are targeted. You see the list at the bottom. On the right hand side, on the top, you see an overview of the Hercules MCU platform, and 3 MCU families belong to this platform, the RM48 family, the TMS570 family and the TMS470 family. The RM48 family is the high performance family and especially suitable for designs according to IEC 61508, and here we have component level compliance up to safety integrity level 3. The TMS570 family is also suitable for designs according to IEC 61508, but additionally appropriate also for designs according to ISO 26262. Below you see a certificate for microcontrollers of the TMS570 family regarding the IEC 61508. This means we have quite a number of safety-enabled components at hand. Some of them are even compliant at the component level, and engineers consider this as a positive thing because it eases their life considerably. And but still, there are some open questions that have to be answered. For example, how can these items be integrated into a safety system? And as we have talked already about software, what is about the software? There is some software, right? The engineer in our slides is a smart engineer. He thinks, yeah, maybe there is an evaluation kit available that helps me to answer these questions. And I have good news for this engineer. There is an evaluation kit available, the SafeTI HSK. And the SafeTI HSK consider everything to get you started: an evaluation board, a safety demo application, an RTOS, a GUI, the Code Composer Studio from Texas Instruments, source code, as well as user-friendly documentation. And when you have worked with the SafeTI HSK, you should be familiar with the Hercules Safety MCUs, with the corresponding companion chips, with the structure of safety software, how the SafeTI diagnostic library is applied, and the ability of the kit to inject errors into the system and to monitor the system behavior should additionally give you insight. Now we come to the SafeTI HSK in a little bit more detail. In the gray box you see the SafeTI HSK board. And we have on this board a Hercules safety MCU and the corresponding safety companion chip. And these both in combination can be considered as a safety base. And our evaluation is targeted towards this safety base. The safety MCU is executing a safety software stack. And we will come back to the software stack in a few minutes. There is a second Hercules MCU on the board. This MCU has no safety connection, but it is used to inject faults into the safety base and is also used for monitoring the behavior of our safety base. Additionally, it implements the communication with the host control GUI that is executed on a regular PC, and you can select errors that are to be injected into the system, and you can also observe the system behavior in a comfortable manner. Now we dive a little bit into detail regarding the Hercules MCU platform. The Hercules MCU platform uses a safety island approach, which has a strong hardware focus in order to maximize performance and in order to reduce the software overhead. And first there is a set of core elements defined. The CPU, SRAM and interconnect are part of this core set, and the core set elements are protected by hardware, and one can be sure that when the core set elements work correctly, then the execution of software is correct as well, and then we can use software-based diagnostic afterwards in order to guarantee the functioning of other devices like peripherals. And overall, this means we have a good balance between hardware and software diagnostics, and we can manage cost concerns. Now I want to introduce you to some of the safety features of the Hercules MCU platform. First, we have a dual-core lockstep CPU. We have two Cortex-R4F CPUs working in lockstep mode, and both are executing the same program, and the results are compared. Then we have flash and RAM that is protected by ECC logic. We have a DMA module with a built-in MPU. There is a CRC controller. There is a PBIST module, a programmable built-in self-test module for testing on-chip memories. You should memorize this PBIST because we will come back to the PBIST in a second. And there is the LBIST, a logic built-in self-test module for testing the ARM CPUs. The last module I want to mention here is the ESM, the error signaling module. The error signaling module collects all the errors that occur within the Hercules, and then propagates this information to the outside world or causes an interrupt. Now we come to the safety companion. The safety companion, first of all, is a power supply that is specifically suitable for safety applications. It does supervision of voltages and uses a reference voltage to do this. There is also self-diagnose modules included. We have a Q&A watchdog that implements a Q&A communication with the MCU over SPI. There is an error monitor which monitors external MCU error conditions, and there is a reset and enable block that does MCU reset, MCU boot, as well as enabling and disabling the equipment under control. And now we see the entire safety base consisting of the safety companion and the safety MCU. We have said that the safety companion delivers the supply voltages for the safety MCU. Both chips talk to each other via a Q&A watchdog protocol over SPI. The NESM error output of the ESM goes to the error input of the safety companion. The NReset output of the safety companion goes to the power and reset input of the safety MCU. And the enable driver output of the safety companion goes to the external power stage, that means to the equipment under control. Okay, this was the hardware. Now we come to the software part, the software that is executed on the safety MCU. You see at the bottom the Hercules safety MCU, and above we have a hardware abstraction layer, and this hardware abstraction layer was generated with the Hercules tool from Texas Instruments. On the left-hand side, we have the SafeTI Diagnostic library and the TPS library. These libraries enable MCU self-tests and communication with the safety companion. We have SafeRTOS, pre-certified RTOS, and on the top we have the safety demo application. And now we go a little bit into detail regarding the different parts of the software stack. First, we will consider the SafeTI Diagnostic library. I have talked about the PBIST and the LBIST. There are more diagnostic modules within the Hercules, and these can be configured with functions within the SafeTI Diagnostic library. Additionally, the library can detect failures during the boot phase, and it can further process errors that are indicated by the ESM and forward this information to application functions that can take further steps. And maybe most important, there are self-tests included in the SafeTI Diagnostic library, self-tests, for example, for the CPU, for the SRAM, for the power state controller, and more. And yeah, we have talked about the Q&A protocol between the Hercules MCU and the corresponding companion. The TPS library supports you in implementing this protocol. Now we come to the SafeRTOS. The SafeRTOS is a safety certified real-time kernel for embedded 32-bit microcontrollers. It is pre-certified by TÜV Süd according to IEC 61508, and we reach a safety integrity level of 3, which is the highest safety integrity level for software. And the SafeRTOS allows us to structure the application as a set of autonomous tasks, and this means we can reduce the dependencies between the different parts of the system. And the system functionality is then the sum of the functionality of the different tasks. Interesting is that SafeRTOS offers MPU support. Overall, SafeRTOS delivers a high level of performance with a minimal footprint. Now we come to the safety demo application. You see the tasks represented as yellow ellipses. These tasks are now running on the SafeRTOS. On the left-hand side we have 3 interesting tasks. We have at the bottom the watchdog service. This task implements the Q&A protocol with the safety companion, and this task uses the TPS library to implement this communication. In the middle we have the safety library server which does periodic tests of the Hercules MCU, and here the SafeTI diagnostic library is used. And at the top the fault injection handler which injects faults into the system, and for the implementation also the SafeTI diagnostic library is used. Okay, now we come to the SafeTI HSK demonstration. We are almost there, but we are not quite there, because I want to first show you what we are going to do. That is the understanding. What we want to do is a PBIST profiling. I have talked about the PBIST module before. The PBIST is a memory built-in self-test engine that tests different on-chip memories within the Hercules, and you can select different test algorithms. You see the module at the bottom on the right, and it has the host processor interface over which it can be configured, and you can start the corresponding test. Interesting is that memories can be accessed with maximum speed, and the PBIST controller has dedicated paths to the memories specifically for the tests. And one question we are going to answer is, how long does it take to execute a specific PBIST? The second thing we want to do is a fault injection into SRAM. I told you before that the SRAM is protected by a ECC logic, and the procedure is as follows. We turn off the ECC logic, then we change a memory location, turn on the ECC logic, and then we read from this memory location. And the interesting question now is, how does the system behave in the case of an ECC error? And now we come to the demonstration. Okay, here on the right hand side you now see the SafeTI HSK board. Here we have the control MCU, here we have the safety MCU. Between both Hercules devices there is logic for fault injection. Above the safety MCU we have the safety companion. Here is additional fault injection logic. Interesting may be, we have here a temperature sensor. On the back side there is an accelerometer. We have here a CAN interface. We have here a TI motor control interface, a 20-pin JTAG header for debugging the safety MCU. And most important, on the left hand side we have a micro USB interface which is used to debug the control MCU as well as the safety MCU with the Code Composer Studio, and it's additionally used for the communication with the host control GUI which we see here. And now I connect the host control GUI to the board and change to the diagnostic settings. We want to do the PBIST test. We select we can select, for example, the PBIST ROM. Then I select here an algorithm which is used for test and a memory type. Then we apply the settings. And then I go to the validation and profiling page, select the profiling tab. Here we do the PBIST and we get the result. This test takes 121 microseconds, and now we compare it to a different test. We select another memory, for example the memory within MIPS by 3, take a different algorithm, 2-port memory, we apply the settings, and then we go back to the validation and profiling page and start the profiling again. We received the result 494 microseconds for this test. So you can find out how long does a specific PBIST take. And now we come to the second thing. I wanted to show you the fault injection into the SRAM. We take the select the fault injection tab, then we select SRAM. Data ECC is already selected, and we inject. And now we get a nice graph showing different signals over time. At time 0 we inject the fault into the system, and the ECC logic detects this fault almost immediately. And then this information is propagated to the ESM module, to the error signaling module within the Hercules, and the error signaling module takes the NESM error pin which goes to the TPS, takes this low. So the TPS, the safety companion, is informed about the error and enters almost immediately a safe state, and the TPS also takes the enable driver output low in order to put the equipment under control into a safe state. And you see that you can do a lot of different fault injections here. You can profile a lot of different algorithms. Maybe interesting is that you can adapt the behavior of the system with the global settings. For example, you can change the behavior of the ESM. You can change also the behavior of the safety companion, and you can adapt the system load. Additionally, interesting, we have application page where you can see the temperatures and the acceleration that was measured. And for those of you who want to do their own developments, we have included the Code Composer Studio project into the kit. For example, we see here the kernel source folders which contain the SafeRTOS. Here is the SafeTILib folder that contains the SafeTI Diagnostic library with corresponding headers. Here we have the TPS library also with corresponding headers. In the source folder we have main.c, and under tasks you see the tasks that are running on the SafeRTOS, and we have already discussed some of them before. Now we come to the summary. I think with the SafeTI HSK you have everything to get started with the development of safety-related systems based on Hercules devices. You have an example safety application. You can evaluate the SafeTI Diagnostic and TPS libraries from Texas Instruments. You can do the measurement of test execution times. You can inject errors into the system and monitor the system behavior, and you can do this with a very comfortable GUI. And also a user-friendly documentation is included in the kit, and the kit is available from the Hitex webshop at ehitex.com for €399.